let's move on to the next talk. So, Laura, could you share your screen?
Yeah, sure.
And yeah, next we'll have Laura Keating, and she'll tell us about proximity zones. Laura,
Great. Yeah. So I'm just going to tell you about some work that I've been doing recently, trying to model proximity zones at redshift 6, and what that kind of means for the growth of black holes. And so first of all, what is a proximity zone? So this is just an example of a quasar spectrum at redshift 6. And as has been shown many times, the Lyman-alpha forest is very saturated at this redshift unexpectedly, or expectedly, but close to the emission of the redshift, emission redshift of the quasar, there's a lot of ionizing photons coming from the quasar itself. And this allows for a more highly ionized intergalactic medium in the vicinity of the quasar. And so you can actually get a transmitted Lyman-alpha forest close to the emission redshift of the quasar. And this is called the near zone or proximity zone. And what's cool about these proximity zones is they're sensitive to how long the quasar has been shining for, especially if it's like in the early phase of this. And so this is a plot from a paper from Christina Eilers showing the evolution of the proximity zone size as a function of quasar lifetime. And in gray here are results from sightlines from cosmological simulations post-processed with the radiative transfer code to mimic ionization by the quasar. And what you see is for shorter lifetimes, less than 10 to the 5 years or so, you find that the proximity zone grows with as the quasar has been shining for longer. And then eventually you reach this equilibrium value, which is set by the ionizing background in the IGM, where you're not so sensitive to the quasar lifetime anymore. And you can take an observed proximity zone size, which is shown by the red dashed line here, and compare this with the results from your simulations. And you can get a constraint on how long that individual object has been shining for, which is pretty neat. And so how did the observations look? So Christina Eilers has really spearheaded this in the last couple of years, putting together a really nice sample of observed proximity zone sizes. And so this is how a sample from her 2017 paper looks, with proximity zone as a function of the quasar magnitude, and the colors of the points are just the redshift of the objects. And so I can plot this equilibrium proximity zone size that I mentioned before on top of this. And what you see is for most of the proximity zones, it seems like a pretty good description. Like there's a bit of scatter, but they all kind of sit around it. But there are some objects that are really far away from the equilibrium value. And in subsequent papers, Christina showed that, this isn't an unusual occurrence. About 10% of quasars in this redshift range have these small proximity zone sizes. And since a small proximity zone means the quasar maybe hasn't been on for very long, this is maybe a population of kind of young quasars. And so this is exciting because maybe it can kind of give you some idea about how these black holes are growing already at redshift 6. So Christina also had a really nice paper out on the archive last week showing the quasar lifetime, different constraints on the quasar lifetime over a large redshift range using different methods. And the proximity zone constraints are all shown here in blue. And you can see that the quasar lifetime can be, 10 to the 7, 10 to the 6 years, all the way down to below 10 to the 3 years. And this is maybe challenging for trying to understand how to grow these black holes, because these are really rare objects, like 10 to the 9 solar masses already at redshift 6. So you're going to have to have been accreting for a long time to grow that black hole already. So how to reconcile this with this very short proximity zone size is kind of tough to understand. So the first thing, we decided we'd go and try and look into this a bit ourselves. And the first question we thought about was, a lot of this work has been done using simulations with a uniform UV background where the IGM is already ionized. But what if there's still a lot of neutral gas in the IGM at redshift 6? And this is some work that I've been involved in over the last couple of years, showing that you actually need a significantly neutral IGM still at redshift 6 in order to match constraints from the opacity of the Lyman-alpha forest. And this is just an example from one of the radio transfer simulations we ran to show this. So this is just a light cone through the simulations. The x-axis here is redshift, and the colors of the image represent how neutral the gas is. So if it's blue, if it's ionized, it's red if it's neutral. And the red box here just kind of illustrates where the redshift range of these observed small proximity zones are. And so there's still a lot of neutral gas in this redshift range, but mainly hanging out in the voids. So we took sightlines through the simulation, and again, post-processing with a radiative transfer code to account for ionization by the quasar itself, to try and see, could we actually match these small proximity zones? The answer was no. So again, we have this plot of proximity zone size as a function of quasar magnitude. The blue band is kind of the median result we get of each magnitude bin, and the shaded regions are like our 1 and 2 sigma contours. And we totally miss these small proximity zones. So they are very hard to reproduce in cosmological simulations, which has already been shown by other groups. But I think crucially here, even in models where reionization ends late. So the next thing we thought was, well, when we ran these simulations, we just assumed that you had one source and it was always on for like 10 to the 6, 10 to the 7 years. But of course, that might not be the case. Things can turn on and off. And we're not the first people to have suggested this. Fred Davies had a really nice paper back in 2019 putting out this idea, but we decided to look into it a bit more. And so this is an example of how this looks. So the black dashed line here is for a source that's on all the time. And you can see the proximity zone grows initially and then kind of settles to one value. And in contrast, we have a source that turns on and off. That's the blue line. And you can see that in this case, when the source is on, the proximity zone is very close to the equilibrium value that is found by the constant model. But when the source turns off, all the gas close to the quasar recombines and the proximity zone becomes smaller. So you can get this evolution in the proximity zone size with the quasar luminosity. And by just playing around with some of the parameters in these Choi models, like how long the quasar has been on for and what the duty cycle of these bursts are, you can come up with something that kind of doesn't look bad compared to the observations. So the black here is a histogram of the observed proximity zone sizes just in one magnitude bin. The orange is for this constant model, and the blue is for a time-varying model. And you can see that the mean of the two simulated models isn't so different. They kind of both peak at about 5 megaparsecs. But in the time-varying model, you get this nice tail of proximity zones that go out to quite small sizes that look reasonable compared to the observations. But of course, things that just turn on and off completely also aren't very realistic. We can expect it to be more stochastic. So we've also been looking in cosmological zoom simulations that self-consistently grow 10 to the 9 solar mass black holes. And this is work led by Tiago Costa at MPA. And so this is just an example through the simulation. So you resolve things both on large and small scales. This inset shows the galaxy that hosts the black hole. And the high spatial resolution of these simulations means we can generate light curves at 10 to the 4 year time resolution. And so again, we can look at a movie of how this is. So now in the top panel, I show the magnitude of how this light curve is changing. And on the bottom panel, I show the response to this on the proximity zone size. So the magnitude can vary hugely over a very short time scale. And the proximity zone itself can also change by a few megaparsecs. And we find that kind of in this particular sightline kind of just oscillates between two kind of set points, depending on whether the magnitude is high or low. And so what does this mean compared to the observations? Well, if I go back to this plot of near zone size versus magnitude and compare it to the black, which is the observations, and again, this equilibrium value, if I take all the points from that movie I showed and just put them on this plot, I get the orange. That's just for one single sightline and its evolution. And you can see that the magnitude can change drastically from -24 up to above to -27. And also you can get proximity zones that are very far away from this equilibrium value. And so we can also add in some results from just a handful of other sightlines. So each of these colored points here are just a run of one individual sightline. But what's really cool is even just for a few sightlines, we can really start to fill out the space in proximity zone size and magnitude, finding lots of sightlines that are close to the equilibrium value, but also lots that are really far away. And we end up with this population of small proximity zones with these simulated light curves, which is cool. So we can compare these to a constant model at a fixed time. So taking now a larger number of sightlines and looking at them all at 10 megayears. And again, just restricting ourselves to a narrow magnitude range, the same as the observations. So again, this black histogram shows the observed proximity zone size distribution. And the orange is just a constant model shining constantly for 10 megayears compared to our blue sample, which are flickering on and off and doing their thing. And again, we find that the mean of these two distributions isn't so different. So we still find large proximity zone sizes as you'd need to. But also we still get these nice tail towards the small ones, which again would kind of reduce the tension between the simulations and the observations. I will say that we maybe don't get enough of these small near zones. It's been estimated that they need to be about 10% of the entire population, which I don't think we quite get right. But there's other things that we're still not accounting for. Like there might be, obscured growth might play more of a role. In that case, you could have a shorter kind of on time for the quasar. But I think even more interestingly, there's been a couple of cool papers out in the last couple of months showing the role of the mean free path. And this is a result from George Becker's recent paper showing that the mean free path at redshift 6 is quite small. And this dashed line here is the result from the simulations that I've been working with. So you can see that the mean free path in our simulations is too big compared to what's actually observed. And Christopher Kane had a nice paper and a nice talk yesterday showing that one way to reconcile this difference is to add in kind of a subgrid model for substructure in your simulations. And so that would also help us, I think, to try and maybe boost the fraction of small near zones that we get, as well as these variable light curves. And so I'll conclude here by saying that just because you have a model where reionization ends late, it doesn't mean that you automatically produce a population of small proximity zones. What's maybe more promising is to have these models that can vary with time, and a toy model can already get you a pretty reasonable agreement. But actually models with light curves from simulations that self-consistently grow these black holes can actually show a population of proximity zones that seem in reasonable agreement with the observations, except maybe not as many as observed. So, yeah.
Well, thank you. That was really impressive work. So yeah, if we have any questions, we'll wait for a little bit to see if questions show up on the slide. In the meantime, I guess I can just ask about that one simulation that seemed to oscillate between those two values of the proximity zone. Is that understood? Is that something about the feature of in the code or parameters?
So basically, I think it comes down to what this definition of the proximity zone actually is. So you take the spectrum and you smooth it, and the first time the flux drops below 10%, you say, okay, that's where the edge of my proximity zone is. So in that particular sightline, we found that there was like an absorber that kind of recombined a bit faster. So that drags down the mean flux to that point once you fall below a certain threshold.
Oh,
so you kind of have this value close to the host galaxy, and then another one kind of set by the IGM.
All right, here's a question from Slack. Very nice talk from Yu Xiaochen. How do the models perform in predicting large proximity zones or longer lifetime that are needed to grow these high redshift large black holes?
Yeah, so I think we do find our models do also predict larger proximity zones. So you see the largest ones here are about 8 megaparsecs, and we also don't have trouble reproducing those. I think mainly because these tend to be close to this equilibrium value, which is something that's kind of successfully reproduced by the simulations generally.
But I guess in your histogram, it did seem like you were short at the large zone. Or...
Yeah, I mean, there's also not so many observations, like there's only in this particular bin. So, and I think some of these also have kind of larger error bars. So I think just kind of in a general way, I'm not as worried about the large ones as I would be about the small ones. I'll say that.
Fred Davies asked, how often do you get the binary distribution of sizes for individual sightlines?
Yeah, so I guess looking at this, if you look at this plot, you can kind of see it happening reasonably often. So like say for this brown or purple, you kind of do get these this bimodality, but also kind of then within kind of a cloud, you also have evolution. So yeah, it's kind of messy, I would say.
And then here's a question you sort of answered a bit. Would you say that we're missing small near-zone sizes above the equilibrium relation, or they're just too rare in a simulation to be expected to be observed in current samples?
So you're asking, is there like a population kind of higher that we just don't see?
I think he's asking whether they're missing the object above.
I think the fact that we don't see them either in the observations or the simulations, like you do see sometimes that you can end up in this space, but I think you tend to scatter the other direction more.
All right, final question. What sets the small value of the near zone as compared to the equilibrium value?
So I guess this is kind of related to Ramil's value, like or question. When the magnitude of the quasar dips, the gas starts to recombine, and you end up with a lot more neutral gas close to the quasar. And so this can suppress your Lyman-alpha forest there, and you end up with a smaller proximity zone. And this can either just be kind of more diffuse gas, or it can be related more to an absorber.